Next, we're going to do an application of the chain rule to determine how the speed of sound varies as a function of the altitude in the atmosphere. So there's a couple things that we need to start with. So first of all, the speed of sound in an ideal gas, such as the atmosphere, is given by the square root of gamma RT. So here C represents the speed of sound, and the speed of sound will be measured in meters per second. Gamma is the adiabatic index of the gas, and this is unitless. So for air, gamma has a value of 1.4. R is the specific gas constant. So this is different than the universal gas constant. The specific gas constant depends on the particular gas in question. So the specific gas constant for air is 287 joules per kilogram Kelvin. Now the specific gas constant allows one to write the ideal gas law as PV is equal to RT. Here P is the pressure of the gas. Lowercase v is the specific volume. So in engineering, the word specific often means per unit mass. So this is volume per unit mass. So this is basically meters cubed per kilogram. So literally the specific volume is the inverse or the reciprocal of the density of the gas. R is the specific gas constant, and then T is the absolute temperature. So temperature basically in degrees Kelvin. So an absolute temperature is a temperature system where the 0 point is the absolute zero temperature, so zero kinetic energy in the molecules of the gas. So Kelvin, 1 degree Kelvin is equal to 1 degree Celsius, except it's shifted. So I believe the conversion is you add 270.15. So basically 0 degrees Celsius is equivalent to 273.15 degrees Kelvin. And then 1 degree of each is the same. So 1 degree Celsius would be 274.15 Kelvin, and so forth. So basically the absolute zero, so this is the minimum attainable temperature, is at negative 273.15 degrees Celsius. And that corresponds to 0 degrees Kelvin. So that's the absolute zero possible temperature. The equivalent for Fahrenheit is degrees Rankine, R-A-N-K-I-N-E, but we'll just stick with degrees Kelvin. So 1 degree Kelvin is equal to a degree Celsius, except the units are shifted. So the 0 point of the Kelvin scale is the absolute zero temperature, whereas the 0 point of the Celsius scale is at the freezing point of liquid water. So this is the ideal gas law, and the speed of sound is equal to the square root of gamma RT. So basically gamma and R are constants, and the speed of sound depends on the temperature of the gas. So literally this can be derived, the speed of gas in general is the square root of gamma times dp d rho. So even if you don't have an ideal gas, the speed of sound is always given by the square root of this adiabatic index gamma times the derivative of the pressure with respect to the density. So for an ideal gas pressure is equal to rho RT. So the derivative of pressure with respect to density while holding the temperature fixed is just RT. So that's why we get the square root of gamma RT. So now that I have this stuff, let me clear some space. So we're going to be so our job is to determine dc dh. So where h is the altitude. So temperature itself depends on the altitude. Now the model that is used is that in the lower atmosphere, which is called the troposphere, so this is the Earth's atmosphere, and it ranges from 0 to 11,000 meters in altitude. So that's roughly 36,000, a tad over 36,000 feet. So the first 36,000 feet in the atmosphere is called the troposphere. And the standard atmosphere model says that temperature decreases linearly within the troposphere. So our model for the temperature is that T decreases linearly as a function of altitude. And this assumption is valid within the troposphere. So our result will only apply for the lower atmosphere of the Earth. And then the next section of atmosphere, I believe the temperature is constant, and then it does something else later on. So it's a model for how the temperature behaves in different layers of the atmosphere. And we have some data. So at 0 meters, so let's say altitude, temperature. So at 0 meters altitude, the temperature is 288.15 Kelvin. This is just a standard, this is called the standard atmosphere. So it's just a model of the atmosphere. Of course, on a particular day or in a particular location, you're going to get variability in the temperature, but we'll just use these values for the temperature as a function of altitude. And then at 11,000 meters, the temperature is 216.65 Kelvin. So we see a drop in a little more than 70 degrees Kelvin, which is equivalent to a drop in about 70 degrees Celsius. So it's a pretty substantial drop. So this, in degrees Fahrenheit, both of these temperatures in degrees Fahrenheit, 288.15, we subtract off the 273.15. So that's basically 15 degrees Celsius. And 15 degrees Celsius is equivalent to 59 degrees Fahrenheit. So in the standard atmosphere, we're using basically 59 degrees Fahrenheit at sea level. And then 206.65, so we have to subtract off 273.15. So that's the temperature of negative 56.5 Celsius, which converts to negative 69.7 degrees Fahrenheit. So at an altitude of about 36,000 feet, the atmospheric pressure in the standard model is about 70 degrees below zero in the Fahrenheit system, 56 degrees below zero in Celsius. So when you're in an airplane and you're cruising at about 50 or 35,000 feet, it's quite cold outside on the other side of that window. So negative 70 degrees Fahrenheit. So in degrees Kelvin, this is 288.15 at sea level and 216.165 at 11,000 meters. So to find the slope of this, we're going to do the change in temperature divided by the change in altitude. So this is T2 minus T1 divided by H2 minus H1, so just divided by 11,000. So what we get is 216.65 minus 288.15, which is equal to minus 71.5. I'm just going to divide that by 11. So I'm going to get minus 6.5. Let me put some units here. Degrees Kelvin per meter. Negative 6.5 degrees Kelvin per kilometer. So by dividing by 11 kilometers instead of 11 meters, this is equivalent to negative 6.5 degrees Kelvin per per kilometer. Now if we want to divide by the 1,000, I didn't need to put that into my calculator, did I? Minus 0.0065 degrees Kelvin per meter. So either one. So that is the rate of change of the temperature with respect to altitude. So since we're modeling this as a linear function, I can get rid of all of this. Since we're modeling this as a linear function, we can write temperature as a function of altitude. Well, at sea level, we're looking at 288.15. So this is basically the vertical intercept, and then minus 0.0065 H. So this is the temperature as a function of the altitude, where altitude is measured in meters. So altitude is in meters. So that is the function. So we have the speed of sound as a function of temperature, and then we have the temperature as a function of altitude. So therefore, the speed of sound is a function of altitude as c composed with t of h, right? So it's this composite function. So this is the same as c of t of h. Now we can compute the derivative of, so dc dh, using the chain rule. So it's going to be c prime evaluated at t of h and then times t prime of h. So t prime of h, the derivative of the temperature with respect to altitude, since it's a linear function, it's just going to be this coefficient right there. So this is going to equal, so t prime of h is minus 0.0065. So I'm promoting that to the front since it's a coefficient. So it's just a number, so I'm moving that to the front. And then c prime, well, c of t is the square root of gamma RT. So we have the gamma R is just a constant. So this is basically, we need to take the derivative of the square root of t. And we know how to do that because it's t to the 1/2. So that's 1/2 t to the minus 1/2. So that's 1/2 square root of t. So c prime of t is going to equal 1/2 square root of gamma R over t. Just like that. So c, the derivative is going to be 1/2 divided by 2, and then the square root of gamma R. And then if I replace t with h, I get 288.15 minus 0.0065 h. So this would be the speed of sound, or the rate of change of the speed of sound with respect to altitude. Now the units of this are going to be, well, the speed of sound is in meters per second, and then divided by a change of altitude, which is dividing by meters, the units are 1/2. So this has units 1/2. So it's basically how much the speed of sound changes per meter increase in altitude, and it's just given by this formula right here.